My name is Afan Putra from the University of Leeds. In this occasion, I would like to talk about how AI can be useful in some CMR applications, particularly in the flow MRI. I do not have any financial interest to disclose. Let me begin with this diagram. So this diagram shows us how AI can be used in different aspects of CMR processing pipeline, from patient scheduling, acquisition, image reconstruction, to the segmentation and quantification, up to the reporting and to prognosis. For example, during acquisition, we've seen some works that AI can be used to predict the full image reconstruction from a very sparse case space. In this talk, I would like to focus on this part, the quantification and segmentation, or the post-processing of the CMR. I'm going to show 3 examples of CMR applications. One is AI in the 4D flow MRI, where we can increase the resolution of the 4D flow MRI while suppressing noises in the non-fluid domain at the same time. And this will allow better quantification and blood flow characteristics and hemodynamics inside the heart chambers and the great vessels as well. In the second application, I will show how AI can automatically predict strain from MR tagging. This is quite challenging task actually, because although tagging patterns are visible and we can see how beautifully the deformation of myocardium from the MR tagging, the quantification itself is a bit it's not straightforward. In the last application, I'm going to talk about how high throughput data processing of large-scale CMR data, where AI was used to automate the whole CMR processing pipeline for more than 40,000 subjects and generated automatically full cardiac frames of models without any user interventions at all. So let's start with AI in the flow MRI. We have seen some significant improvements of assessing blood flow from MRI. At the beginning, we see from the standard 2D phase contrast MRI that we can estimate the blood flow that run across the image plane, and then we can acquire three directions of the velocity for each pixel of that plane. And now we can get a full 3D volumes of flow MRI, so that we can basically quantify blood flow at any location in a 3D volume. And then we can visualize time resolved 3D blood flow throughout all the vessels and the chambers. And we can measure lots of blood hemodynamics that were not possible with a single plane velocity encoded MRI before. However, with this 4D flow MRI, we get lots of data with an increased complexity of the data itself. And the 4D flow MRI has some limitations. Because of the rapid changes of the magnetic radiance, we see an increase of the eddy current in the 4D flow MRI. So we see an increase of noises. Also, setting the Feng parameter during the acquisition is a bit tricky, because you want to cover the whole range of blood flow velocities, from the slow velocity to the high velocities. If we set the Feng too high, we can't see the low velocities because they look like noise. But if we set the Feng too low, then there will be phase wrapping in some high velocity jets. The other limitation of 4D flow MRI is the low spatial resolution and also the temporal resolution. So to enable accurate blood flow measurements, we need high resolutions of 4D flow MRI with few noises. Now, this is the work of Edward Ferdian. So he is a PhD student at the University of Auckland, New Zealand. He developed this network, which he called it 4D flow net, where it learns how to increase the resolution of 4D flow MRI by using a deep learning network. And also he used computational fluid dynamics to generate the training data. His network was based on the super resolution net. This is a common network used by the computer vision community to increase the resolution of an image. And we can see how good the super resolution net compared to, for instance, the bicubic interpolation method. So based on this network, based on this idea, Edward developed this 4D flow net. The input of the input of the network are 4 images from the 4D flow MR sequence, the magnetic, and the 3 velocity encoded images. And then through some deep convolutional layers, he tried to predict for each direction the high resolution of the velocity. But there is a problem with this. I mean, this is the same problem with all deep learning network, that it needs lots of training data. With this network, we need to have a pair of low-res and high-res 4D flow MRI, which is not financially feasible. The cost of it is too expensive. So we tried to find a different way to generate data for the training. And we came up with this solution. So we used the computational fluid dynamics to simulate the flow velocity from a certain geometry. In this case, Edward took the aorta from a challenge, from the Stockholm challenge dataset a couple of years back. Now, to make the data agnostic with the geometry, instead of learning from the whole structures, the network learns only from the small patches of 16 by 16 by 16 pixels, as we can see in these images. In this way, the network can learn the velocity flow in any direction, in any geometry. Then after that, we put that high resolution of the velocity field into the downsampling process. The downsampling process, we use the same way as what we had in the MR. So through some Fourier transform, added noise distribution based on the MR noise distribution, and then back to the inverse transform to get the low resolution images. And then we trained the network with lots of training data with this approach. This is the result with the bifurcation phantom. So we have the pair low-res and high-res images of the flow field. And then we compare what the higher resolutions of the MR with the prediction of the 4D flow net. And as we can see here, based on these 2 resolutions from the 2mm and 1mm resolutions, the 4D flow net predicted quite good results. And there is one additional bonus with this network. It is that it suppresses the noises automatically. So we see the higher resolution of velocity field without any noise, especially in the non-fluid area. So this is good. Now we try that with a patient data. So this is a patient, congenital heart disease patient. We do not have the high resolution for the flow net, so we compare that visually, as we can see here, and we can see that the 4D flow net predicted quite good. It suppressed the noise significantly, so that we can only look into the flow field inside the aorta and the other vessels. Comparing with other interpolation functions, the 4D flow net predict better than, for instance, the linear, cubic, or sinc interpolation methods. In the non-fluid domain, we see that there are noises in the interpolation methods, but for the 4D flow net, it removes all the noise. Also, we can see inside the fluid domain itself, in the vessel, the prediction of the 4D flow net is quite good. And the errors for the 4D flow nets are the less. Now, there are some other works of AI in the flow MRI, so I can show you here three published papers that are interesting. The first one is the work of Valery Vishnevsky, that they developed a network to construct or to reconstruct the 4D flow MRI so that the acquisition time can be reduced significantly. The last two are the interesting direction of the deep flow, the deep learning network in the physics, where they try to induce or to create physics-informed neural nets to estimate the flows. I think this is going to be the next big thing for flow reconstruction or flow visualization. Now let's go to the AI for the MR tagging. This is also the same work of Edward, but he developed another network for calculating strain for MR tagging. In this case, we use the UK Biobank data. So the network was trained from more than 4,000 cases of the UK Biobank. The initial contours were generated by a dedicated SIM software, and 5 readers corrected contours at 5 different frames at ED and diastole and systole, peak filling, and at the end of the cycle. And the training was done to train 2 sub-networks. One network is to automatically detect the region of interest, so the bounding box of the myocardial. And then the second subnet is to track the patterns movement from the tagging MRI. So here's the diagram of the networks, 2 subnets concatenated serially like this. So the first one is to localize, and the second one is to track. And this network, the whole network was trained in the whole, so it's the end-to-end training. And here is the result for one prediction from the MR tagging. We can see the ground truth at the middle and the prediction of the tag patterns on the right side. You can see that visually it correlates nicely, and we can calculate the strain from that, and the errors of the strains are comparable with the manual calculations. So this is one example of CMR in MR tagging. The last example that I would like to show is the AI in the large-scale CMR data. So this is the work of a group in Leeds. So they have built an automatic pipeline to quantify CMR images from large-scale data. So in this paper, they reported for 20,000 subjects, but currently they have already processed more than 40,000 subjects. So the pipeline was developed on top of the Multics platform. This is a platform that can that allows researchers to run and compute a lot of processings for images. We see here from the input to data organization, and then to the image quality assessment. So in this image quality assessment, we used deep learning nets to detect whether the images are good or not based on the full coverage of the heart. And then the organ detection, the initial estimate of the model, fitting the model to create the segmentation and to create a 3D model, and then to do the quantification, and then the assessment of the segmentation quality. So the whole process of this were done automatically without any user interventions at all. So here's the snapshot of the pipeline integration. So the last report that they had, they processed about 32,600 subjects. Each subject contains 50 time frames. So in total, there are almost 2 million of images being processed. And these were done automatically and finished completely in 2 days. So this is how AI can be useful to process the whole large-scale data. And these are some examples of the models, the left and right ventricular models after the fitting to the MR images. All right. So as a summary, AI is obviously helpful, very helpful to improve the workflow in clinical MR settings. We've seen many methods, AI methods being proposed to improve the processing time and also the accuracy in the clinical image processing, not only for the cardiac. Many of them are classical segmentation and classification tasks, but beyond of those tasks, AI can be used actually for some targeted purposes. For instance, in the flow dynamics that we've seen in this presentation, or in other biophysical measurements. Also, AI is definitely useful for a fully automation in the large-scale population studies such as the UK Biobank. Okay, and thank you for your attention.